Let us now actually go ahead and solve this equation exactly. Now, to solve an equation of this form, it's a differential equation. It has the same type of form as the capacitor equations that we've seen in the past. Specifically, it is a separable differential equation, which we can solve by arranging all of like variables on one side of the equation or another. In this case, what we can do to isolate the currents I is to divide both sides by E minus IR. That will put all of the currents on this side of the equation. And then on the other side of the equation, we can move dt, keeping time separated from I, divide through by L, and then we will have a nice separated equation. So let me write that down. If you recall what we just said, we will have di, but then I'm dividing by E minus IR, and that equals, I'll leave a little space so I can write some integral signs, that equals then, as I recall, 1 over L times dt. Here we can double check my algebra. We can't see them at the same time, but I think it's pretty clear. Di over E minus IR is what I've written here. L moved on the other side of the equation and went on the bottom, whereas dt went up top. So, at each time interval, there are changes occurring on both sides of this equation, and they line up perfectly. I then can add up all of those little changes, in other words, integrate them. And because I'm adding up specific values, I am talking about definite integrals. So we need to place the appropriate limits of integration. We know that at the beginning of the process, as we've said, because of this continuity argument, the current starts out at 0, and it's going to end up then at whatever value it has at time t, I of t. On the other side of the equation, my integration variable isn't current I, it's time t, and time t runs from t equals 0 to whatever time t we are considering. And finally, to keep the mathematicians happy, as we always like to do, this integration variable shouldn't have the same name as our limit of integration, so we can call that a dt prime. So, now we have just a mathematical or integration problem to carry out. I think we can handle certainly the right-hand side here pretty easily. The integral of a constant times t prime, dt prime, is t prime times my constant, integrated between 0 and t. So this gives me t over L, when I substitute t prime equals t, minus 0 over L. And of course, 0 over L is just 0. We don't have to worry about that term. On the left-hand side, over here, we see we're integrating a reciprocal. So the antiderivative of that should give me back a logarithm of E minus IR. Now, to get the prefactors, we need to take the derivative of this with respect to current to make sure we recover the original integrand. When we do that, of course, we get our denominator, E minus IR. But when I take the derivative of this with respect to current, I get an additional factor of minus R, which I don't want. So to get rid of that, I have to multiply by minus 1 over R. And finally, this has to be evaluated between 0 and the current I. Minus 1 over R is just a constant, so I can factor that out. And then I have to write my limits of integration between 0 and I at time t. And then this will equal just time t over L. And at this point, what we have really boils down now just to some algebra and some substitutions. So I'll try to do this a little bit quickly. You can check along with yourselves if you like. But you'll notice what I'm going to do is I'm going to multiply both sides by minus R, and then I'm going to exponentiate to get rid of the logarithm. So on the right-hand side, I'm going to have e to the minus RT over L. So this is definitely some kind of exponential process. And then I'm going to be exponentiating this logarithm with I substituted in, and subtracting this logarithm with 0 substituted in. And of course, the difference of those two logarithms will be the logarithm of the ratio, but I've exponentiated everything, so I get just the ratio. The first part of the ratio is when I substitute in I, so I have e minus I of t times r. And then when I substitute in 0 to get the bottom part of the ratio, that would just be e. And finally now, we need to solve this for the current. And the way we do that is we multiply by e. So I'll have this EMF times my exponent. Then I'll move IR to the other side of the equation, where it will come in with a plus sign. The term here that has the e and the exponential will go to the other side of the equation with a minus sign combining with this e. And then finally, I divide by r to get the current I. So if you've tracked all that, or you can check it on your paper more slowly yourselves, but you'll find then that I of t has to equal, I have the r I'm dividing by, and I have these common factors of EMF. So it's going to be EMF divided by r. And then what was left over was one copy of EMF minus a copy of it times this exponent. So it's going to be 1 minus e to the minus rt on L. And that will be our final solution. So let's just check. Let's just check our guess. See how good our intuition was, and this also allows us to build some confidence that we actually have the correct answer after all of that algebra. Let's check now. As t goes to 0, the current, I at 0, is going to equal, well, when t is 0, I get E over R is my formula, times 1 minus, and e to the 0 is just 1. And 1 minus 1, of course, gives me 0. But 0 is what the initial current had to be. So that worked out very nicely. How about then when time goes to infinity? In that case, if we substitute in infinity for time t, I'll have E over R times 1 minus. Now when t equals infinity, I get e to the minus infinity, which is 0. And 1 minus 0, of course, is just 1. So what I get in this case is just the EMF over R, which is what we said we would get if the inductor was just a wire. So I think we can be very happy with our solution. I think this is definitely worth a happy professor symbol, because now we have a very clear idea of how to solve for the currents in standard LR type circuits.